Hello and welcome to NASA Science Live, an opportunity for you to come behind the scenes and get to know your space agency. I am your host, Scott Bednar. Okay, today is all about black holes. Do you have questions about these mysterious cosmic giants? Then I have good news for you. NASA Science Live is your chance to interact with NASA scientists by sending your questions directly to us. It's easy too. Just visit us on Facebook or Twitter and ask us a question using the hashtag AskNASA. Or you can leave a question in the comment box wherever you're watching this program today. Okay, so let's get sucked up into black holes. Not literally, of course, because we would die. Figuratively. We're going to discuss what black holes are, how they work, why they exist. I mean, have you ever wondered what would happen if you fell into a black hole? Have a nice trip. See you next never. We've got black hole experts lined up for you, and we'll even take you on a tour of a telescope that flies the friendly skies. But before we take off, please be seated, fasten your seatbelts, and take note of the nearest exits as you give your attention to this short black hole safety video.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kind of bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't all that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly, so the chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
Well, that was adorbs. I'm obsessed. Maybe our little alien friend will join us a little later in the show. Okay, let's dive right into black holes. Again, not literally. I am joined by two NASA scientists, Bernard and Shubhashish. Thank you both so much for being here today.
Thanks so much.
All right, let's get started. So I feel like a TV show about black holes would not be complete without asking, what is a black hole?
That's a big question, Scott. Yeah, so black holes are just like any other massive object in the universe. It's just that the mass is so much condensed into a small volume that the space-time around it is warped so much that not even light photons can come out of it. So to imagine if sun is compressed, the same mass of the sun is compressed to a volume of 3-kilometer radius, it would become a black hole. And if the Earth is compressed to this volume, it will become a black hole. And not even light photons could come out of it. But the gravitational effect around it would be the same.
So astrophysically, black hole is usually the endpoint of, say, a dead star. After it's used up all its fuel, it gets compressed down to a tiny, tiny space.
So I understand you have a demonstration set up over here that can help us better understand black holes. We have a lot to unpack. So you want to show it to us?
Sure.
Okay, great. Well, while Bernard is setting up his demonstration, remember that you at home can send in your questions using the hashtag AskNASA, or just type them in the comment box wherever you're watching this. All right, Bernard, over to you.
Okay, thank you. So this here is what we call our spandex spacetime. It's the way we visualize how gravity works, according to Albert Einstein. And so before Einstein, we thought gravity was just like a force between two massive objects like stars or planets or whatever, and it was very strong because they were quite close together and because they're so massive, and it was direct interaction. Einstein said that wasn't quite right. So really what you should think about is space itself playing this central role. So instead of space just being kind of unchanging, space is kind of warpable, it's deformable. You can actually bend it and it has an effect. So if you took, say, a small star just traveling through space on its own, not near anything else, it would just go in a straight line, just through space. But if for some reason there's something very massive nearby, some very dense object like a black hole, sitting in space, what it does is it warps a space, it bends it. Now any object trying to move in a straight line can't move in a straight line anymore. It's going as straight as it can, but it looks like a curve, just like that. And if the object is kind of very lucky, it can get caught in an orbit just by having an orbit or a path that's continuously curved around the central object. And that, in fact, is how our own solar system works. Our planets orbit around the sun because they feel the slight curvature that the sun makes around it. And that's how gravity works. That is gravity. And it has some other interesting side effects. So not just planets and small objects, but even light itself can be affected. So if I had a very distant object in the universe, say a quasar, some very, very bright, very distant object, and I'm trying to look straight at it, but there's something like a black hole or some other dense object in between, the light straight from the quasar doesn't come to me. It hits the black hole, it's absorbed. But the light that would otherwise go just past me to my right or to my left is actually bent in back toward me. So instead of seeing one image, I see a few images, or even a whole smeared out ring of images of this one thing. And this is something we call gravitational lensing.
So this is really helping put things in perspective. So this is showing how black holes interact with their surroundings, and that's how we know they exist, even though we can't see them?
So that's one way we have of knowing they exist. Another way, kind of related, is if instead of this black hole being far away from other things, if it's part of a binary star system, its companion, which might be a normal star, it's not as compressed as a black hole, and as it orbits around the black hole, bits of its outer layer can be ripped away, and they can end up orbiting the black hole itself in a kind of a disk of gas, hot gas. It gets very, very hot and glows very, very brightly, and that's also something that we can see.
Well, thanks for clearing that up a bit. So it wasn't that long ago that the first ever image of a black hole was revealed to the world, and it was incredible. Shubhashish, Bernard, how is it even possible to capture a photo of a black hole?
I should start off with saying, like, hey, black holes, now we can see you. So that's I think it's a stupendous achievement on the part of physicists to actually see a black hole shadow. So what we see is actually the accretion disk in the background and the shadow of black hole as a black spot around it. So it's the event horizon of the black hole, and it is a central active engine of the galaxy M87, which is an elliptical galaxy, which is a nearby active galaxy. What do you mean by active? It's not like the Milky Way, for example. Milky Way has a supermassive black hole sitting at the center, but it's accreting less effectively. So it's not accreting as fast as M87. M87 is very, very bright in the center, and so the engine is very bright at the center. So we see the black holes in the backdrop of the central engine.
It's still such an incredible photo. If you're not impressed with the first picture of a black hole, then clearly you don't understand the gravity of the situation. All right, Bernard and Shubhashish, don't go anywhere. I've got lots of questions for you coming up. As you have heard earlier in our black hole safety video, if you stay far away enough from black holes, they aren't that harmful, which is why Earth isn't being sucked into a supermassive black hole as we speak. Now, we have a very special guest, live and in Technicolor, our very own alien traveler. Oh, looks like he's not in frame. If you could just back up a little bit. Oh, welcome. Thank you for joining us today. So, you just recently took a trip to a black hole. That sounds dangerous. What did you see? Oh, we've got a phone. Perhaps an Instagram feed. What are we looking at?
Well, looks like he actually got very close indeed to a black hole, kind of an active one. It looks like it has an accretion disk, and it has some kind of jets coming out top and bottom. So it's really it's making a lot of stuff happen nearby.
So, Traveler, did it feel different near a black hole? Sounds like a good question. More photos?
Wow. So it has been very hot near the black hole, so 1,000,000 degrees Kelvin. So it means that the black hole is, the radiation is very, very, very high in the near regions of black holes. And it tends to happen that smaller mass black holes and the stellar mass black holes emit in X-rays. So this would be few times the mass of the sun. The black hole's mass would be like the stellar mass.
So, a small black hole as black holes go.
Yes,
Yeah.
as black holes go. Yes. Yeah, sure.
All right, Traveler. So I've been told that time actually acts differently near a black hole. What does that feel like, time being different? That's a good question.
Oh. Okay. It looks like he was taking care of a plant just before his trip. A baby plant. He got back after just a day or so, and yet it blossomed up into this fairly huge tree. I think
Beautiful
a
tree.
lot more time passed out here, far from the black hole, than did for him when he was close in.
So time is actually different near a black hole.
Actually different near a black hole. So if you go very near the black holes, say 10 years, there would be equal to, say, thousands of years on Earth. So you can actually live longer. If you want to live longer, go to a black hole. Don't jump the event horizon, though.
I'll look into it. All right, Traveler, thank you so much for joining us. It's been an absolute pleasure. Perhaps you can look for a less dangerous vacation spot next time. I hear the Caribbean's nice this time of year. So we've got some questions coming in from you at home. If you want to get your questions in, please send them in using the hashtag AskNASA or comment in the comment box wherever you're watching this. All right, here we go. So Hilario Pena on Facebook asks, why is it that even the light can't escape from a black hole? Why can't light escape from a black hole?
So it's kind of an extreme version of what the Traveler just experienced. Time actually ticks more slowly as you're close in to the black hole, and it's just the nature of black hole space-time, and this is continuously getting slower and slower, and the event horizon is right where it slows down to a standstill. So if you're there, you might think time's going really, really quickly, but as far as anyone distant from you in the safe part of the universe is concerned, you're not doing anything at all. It's just frozen. No signals that you produce can go any further. They can't come out anymore.
It's so interesting. You don't think about these time differences when it comes to black holes. Well, you guys do, I'm sure. So, okay, another question from Facebook. Eric Lamont asks, is the depiction of black holes in Interstellar accurate with regards to how it would actually look?
Absolutely, yes. And I should remind everybody that it was done by none other than Kip Thorne, the Nobel laureate. So it has to be accurate, of course. And maybe Bernard can say about the NASA's depictions of the black holes videos that we see in the behind screen.
Sure. Well, so that depiction in Interstellar was actually very, very realistic. And as Sebastian pointed out, a lot of trouble was taken over it. And in fact, they wrote a book about how they took pains over the science to get it working right. We do have locally produced videos that kind of go a bit more into it. They can actually give you a flyby of what it looks like if you're kind of seeing this accretion disk around a black hole from different angles. So it's not just at one angle when you're kind of looking edge on. You can kind of see the whole thing flowing, and the image is distorted differently as you just pass above and below the accretion disk plane. So now we're face on, and now we're kind of going down to edge on and face on again.
It's incredible that we're able to put that together. So we've got more questions coming on a little later in the show. You at home, keep sending in your questions using the hashtag AskNASA. Okay, we've already talked about what black holes are, so let's get into what they aren't. I want to address some of the common misconceptions about black holes, and trust me, I cannot do this without you, Bernard and Shabashish. Sure. So I feel like one thing that people think about black holes, I honestly do, is that they're these giant vacuum cleaners in space sucking everything up.
Definitely not.
It's not true.
Not true. Because if you just think of Earth being squeezed to this volume, it will become a black hole. And the surface area of this one compared to the Earth is so small that head-on collision just being squeezed into it is so less. So what happens is a black hole tends to have a gravity the same mass as other objects. So what happens, a particle falling into it will form an accretion disk around it, and it gradually loses angular momentum, and gradually it falls down. To give you some numbers, like a billion solar mass black holes, black hole of the mass of, like, say, billion times that of the sun, accretes matter at the rate of, say, 1 times the mass of the sun per year. So the accretion is very, very slow, so it's definitely not a vacuum cleaner.
So when you say accretion, accretes matter, you're saying the matter that we're seeing in the depictions around it.
Absolutely, the depictions around it. So the matter actually falls in very, very slowly by losing angular momentum at every stage, at every radii, transferring angular momentum outwards, and it goes gradually into it. And just near the event horizon, it just falls into the black hole, and the black hole mass increases. So the black hole grows by this, but it's a very, very slow but energy efficient process.
Wow. Good for black holes.
Yeah.
All right. Well, what would happen if, say, I stumbled into a black hole and fell in?
Well, you'd be dead, obviously. And the way in which you'd be dead is that you would be stretched. So that the black holes exert, if you get very close, they exert enormous tidal forces. It means the gravity acting in different parts of your body is different strength. So if you're going feet on in, then your feet are going to experience a greater acceleration due to gravity than your head, and it's just going to stretch you out like a noodle. So we sometimes call this spaghettification.
Sounds like a rough
nice
day.
term.
Yes.
Yeah.
Not something you want to do voluntarily.
Now I want Italian food. Okay, let's move on to Ask NASA questions, where we are answering your questions from home. So let's see what the World Wide Web is stirring up for you right now. All right, we have Juan Taborda on Facebook asking, what will be on the other side of a black hole? A strange universe?
We don't know. So mathematics breaks down beyond the Schwarzschild radius or the event horizon that we can think of. So we don't know what is inside a black hole. Till date, we don't know. Maybe.
And we may never know. And so our understanding of black holes is due to Einstein. That's a classical theory, so there's no quantum mechanics. But we know if we really want to answer these kinds of questions, we'll have to have a quantum theory of gravity. And that involves general relativity and quantum mechanics put together in some way that we don't have yet. And if we get that, someday perhaps you'll understand a bit more and you'll know what could be on the other side.
Sounds like you have your work cut out for you.
Yeah.
All right, Brandy Valdez on Facebook is saying, oh, my 4-year-old is asking, have we ever sent anything to a black hole?
Not yet.
Would we like to?
Sure, but the nearest black holes are like thousands of light years away from us, if I'm correct. So sending something would take like more than that, so that amount of time. So,
but you could get some cool images, especially if it had an accretion disk or something like that. You could get some very good science out of it, but the spacecraft isn't going to come back again. And a good chance if it falls in, then we're not getting it back.
One-way trip.
Yes.
And we need better propulsion technology.
Yep.
Yeah. All right. Future Spaces on Twitter is asking, how does a black hole begin and how does it end? That's a good question.
Oh, okay. So,
yeah, you can take it.
okay, so black holes, it depends on the size, but black holes that we encounter often are the end point of a star's lifetime. So a star has spent all of its active life burning nuclear fuel, sending light outwards, and gravity pulling back in. And when the nuclear fuel runs out, the gravity starts winning and the whole thing collapses. And if it's a large enough star to begin with, it's a violent enough collapse, you end up with a black hole at the end of it. So that's kind of how a black hole starts. If it's a stellar black hole, larger ones can form without even having a star in between. Just lots of matter just falls into one place at once.
But still, we are trying to find out how massive black holes form and how these supermassive black holes at the center of the galaxies co-evolve with these galaxies. So it's still a big, big question how massive black holes form.
As to the other part of that, how do they end? As far as we know classically, they don't end. Black holes, once they're formed, they can only ever get bigger and bigger and bigger and bigger. Now, if you did have a proper quantum theory of gravity, we might know more about how they could actually evaporate away. This is something Stephen Hawking came up with in the past. So it's called Hawking radiation. It might be a way for very, very small black holes to evaporate and disappear, but we haven't validated that, and
Not quite yet.
It's still unknown.
All right, well, again, more questions to come a little later in the show. So keep sending them in using the hashtag AskNASA or commenting in the stream wherever you're watching this. All right, we've just learned a lot about black holes, but how do we even know what we know about them? It turns out that NASA has lots of missions that study them. One of them, called Sofia, is a telescope that flies in an airplane at 30,000 feet, studying infrared light from cold and distant regions of the universe, including matter around black holes. While Sofia can't see black holes directly, it can uncover their invisible features by studying the material around them. Make sense? Yeah, me either. Let's take a closer look.
We're here at the Armstrong Palmdale facility, which flies airplanes for NASA. And behind me is Sofia, the Stratospheric Observatory for Infrared Astronomy. It's a 747 SP aircraft on which we put a 2.5-meter telescope inside of it. We fly into the stratosphere above most of the water vapor so that we get a clear view of the universe in the near and far infrared, things that you have to go into space to do otherwise. We are only now in our 5th year and the best observatory in the mid and far infrared region. Okay, they're getting ready for flight, but let's go on up. Now we are inside the Sofia Observatory, and of course the most important aspect of the observatory is the telescope, which is way in the back there. That's why the seats are all facing that direction, so that we can look at the telescope to make sure everything is all right. Let's go on up and actually take a look at the telescope. This is the Sofia telescope. Actually, it's the back side of the telescope. It's here in the cavity. The real telescope, the mirror, is on the other side of that white bulkhead. One of the things that we really have done a really good job with on Sofia is studying the radiation that is around our black hole that is in the center of the Milky Way. It's 4 million solar masses black hole. We don't actually study the black hole. They always study the material around the black hole. A black hole, material goes into it, even the light goes in. So you never can see the light that goes into the black hole. You can just see the radiation around it. But with Sofia, we are able to see material circulating and falling onto the black hole. And we have observed it with 4 instruments, and we have the best pictures of what is happening going into our massive black hole, including, most recently, measurements of the magnetic fields that's associated with the material that is falling onto the black hole. It's a great observation that could be only done with Sofia.
Thank you, Eric. I hope you have a very comfortable flight. So, Sofia is just one of NASA's missions that studies black holes. But there are many ways that we observe the effects of these mysterious objects. Bernard Shabashis, I'm coming back to you.
Sure.
Other than Sofia, how else is NASA studying black holes?
NASA is studying black holes with lots of missions. Flagship missions such as Hubble Space Telescope and Chandra has done a lot of work on the accretion disk physics of supermassive black holes and stellar mass black holes, and the winds that are coming from the accretion disk and how they give feedback. And not only that, more recent missions like New Star, Swift, NICER, all our NASA missions have done are doing a great job in understanding the nature of the dynamics of matter near black holes. And to give you an information, today is the 15th anniversary of NASA's Swift mission studying black holes. Today, and I am a Swift mission member, and it makes me proud that we are still trying to investigate more deep into black holes.
Well, congratulations.
Thank you. Thank you.
Here's to 15 more years.
Yeah.
All right, I'd like to know, can black holes, 2 different black holes in different galaxies, merge into one? Is that possible?
They can. We think it happens all the time, except very, very slowly. And galaxies merge eventually. A long time from now, our own Milky Way galaxy is going to merge with the Andromeda galaxy. And each of them has a supermassive black hole in the center. And eventually, after billions of years, they're going to end up in this kind of binary orbit around each other. And when that happens, they are going to gradually contract and merge because the whole system is emitting gravitational waves, which is just another aspect of gravity that Einstein predicted.
So tell me a little more about gravitational waves. I understand we have a demonstration that might help us better visualize.
So gravitational waves they're ripples of space-time itself. Just like it can be warped by single objects, massive objects, you can actually cause little ripples, and it's generally caused whenever massive objects are accelerated through space-time. So here in this demonstration, we've got a tub of jello that's acting like space-time here, and we have a laser shining through it. And what happens when you when you disturb this by dropping this mass here, especially like a second black hole encountering the first is, you're making the jello wobble a little bit like space-time wobbles. And as it does that, the laser beam firing through it, its path gets deflected, it gets distorted. And if you have an instrument that can detect very, very small changes in the laser path, that tells you about the gravitational wave that went through space-time to cause it. And this is basically how we are able to detect gravitational waves.
Oh, it's fascinating and delicious. If you at home want to learn more about this demonstration or use it yourself, just visit go.nasa.gov/bhlesson. All right, let's get back to some of those questions flowing in on the interwebs. All right, we have Coral Riegler on YouTube asking, can any old star or planet become a black hole?
Stars can form a black hole, of course, because that's how the stellar mass black holes are formed. When the star runs out of fuel, the fusion fuel, it just collapses, and then there are stages of quantum mechanics which actually tries to hold them, like electron degeneracy pressure, which holds when it's kind of white dwarf stage, like 1.5 M-sun, and it holds the neutrons degeneracy pressure comes in when it forms a neutron star. But if the star is massive enough that none of these forces actually can hold its gravitational effect, it just collapses to form a black hole. In case of planets, they're already formed, so it's kind of the structure is already formed. So planets forming black holes is not possible.
Not gonna happen.
So not gonna happen. Yeah.
So Earth won't be turning into a black hole.
No.
Okay.
And even then, even when a star collapses to form a black hole, the star has to be pretty big, and it's a kind of, that formation is kind of inefficient. So to produce like a 5 solar mass black hole, you'd actually need something like a 20 solar mass star, because the collapse happens, the center becomes a black hole, and the rest of the material just kind of gets shot out into space.
So good news for us.
Yes.
Okay. Gaurav Sharma on Facebook is asking, is there any estimate in the number of black holes in a single galaxy?
No. So it can vary depending on the galaxies, the star formation rates, and how many massive stars there are, and also like it depends on how old the galaxy is, like elliptical galaxies or like lenticular galaxies or different types of galaxies have different numbers.
Okay. So again, it just could be anything.
Anything.
All right, we've got about 1 minute left. So Cardinal on YouTube is asking, can we see behind or into a black hole? And if yes, how?
Well, we can't see into it because no light comes out of it, but we can sometimes see behind it, and that's a little bit, that's an aspect of this gravitational lensing we're talking about, or these great pictures from M87, this accretion disk. When you see that picture, you're seeing behind the black hole at the same time, because the light gets distorted and bent around in a very strange way. It's a really weird light warping issue.
So we are not seeing the black hole, we're seeing the black hole in the backdrop of the accretion disk.
It's fascinating stuff. I wish we could talk more, but unfortunately we are out of time. So Bernard, Shabashis, thank you so much for joining us today.
Thanks,
Thank you.
We could not have done this without an astrophysicist. Do you at home crave more black holiness? Of course you do. Then just head on over to nasa.gov/black holes to feed that beast. And if you're absolutely obsessed with black holes, like me, then luckily for us, there's another opportunity to get sucked in. This Black Friday, while you're being bit by strangers and fighting a toddler for that last doorbuster deal, consider that NASA will be celebrating Black Hole Friday, a much more science-y version of the post-Thanksgiving hysteria. Just visit us on Facebook, Twitter, Instagram, you know how it works, to get sucked into a veritable smorgasbord of black holes. Until next time, I'm your host, Scott Bednar. Thanks so much for watching NASA Science Live.